Hello, good afternoon, everyone. We are getting started to talk about how to reverse NIM. Let's just get started. First of all, you cannot see my slides, which is not helpful. Okay, here we go. So he's Holger. I'm Vitor. We both work at the Cisco Talos security research from Cisco. And well, he's based in Germany, I'm based in Portugal. And we decided to make a talk about NIM, which probably some of you are not used to this kind of language. So that's kind of why we had actually decided to do a talk on how to reverse NIM. So before we start, some disclaimers. This is a language that is evolving really fast. There are new things being added all the time. There are a lot of tweaking capabilities in the language itself. So some stuff that we are going to present here may not work in future versions, or it might need some little tweaks to make it work. So what is NIM? NIM is it's a language that has taken a lot from a lot of other languages, basically. So for instance, it has an indentation syntax-led syntax, which they picked up from Python. It has all the flexibility of generics from C++. It has all kinds of features that they thought it would be nice to get from other languages, like metaprogramming. All sorts of things that they are really, really cool when you are developing, but they might not be so cool if you are trying to reverse it, because it will generate a huge amount of boilerplate code, which at the same time may be just a little bit of code, or if you switch one flag in the compiler, it will be 3 pages of code, which makes it really hard for you to actually get a good approach on how to reverse it. So this was kind of our objective when we started to reverse this, to find out a way to easily reverse this language, was how can we, for instance, easily define what is boilerplate code from what is user code or programmer code. So that was one of the things that was a challenge for us. So going back a little bit, so it can compile through to all kinds of languages, because one of the things that NIM does, and eventually some people might not like what I'm going to say, NIM doesn't really compile. NIM translates. And yeah, anyone in the community from NIM will kill me now, but let's just wait until we get to the end. So basically what NIM does is that the compiler will write C, C++, or JavaScript code, which then will be compiled by a more common compiler from C or C++, which is good in a sense, because you can do all sorts of optimizations. You can also pass on certain optimizations to the linker of the compiler from C, and you can input a lot of other obfuscation on top of the code that is generated by NIM on C, which kind of becomes a little complex when you're trying to reverse it. It also allows you to develop a lot of other libraries, and it can add more extensions to the C language, which is kind of helpful for if you are a coder. And it has a very, very powerful metaprogramming language like macros, generic types, all that kind of stuff, which is really useful when you are programming and not so cool when you're trying to reverse it. And you will hear me ranting about this all the time during the talk. So this is one example. So you can define, on NIM, you can define generics. So in this case, you have a binary tree, which is of type T, which is whatever you want. And it will only be defined at compile time, the first time the compiler finds some attribution done to this kind of object. So this is a little different from other languages that do this in runtime. In NIM, this is done at compile time. So when actually the NIM compiler is translating the code from NIM into the C or C++ or JavaScript. Also, there is also some development being done to develop a backend to Rust. One of the things that you may ask at this point is, so why should I develop in NIM when I can directly develop in C++ or C or whatever? So on one side, this is used a lot to generate code that can then be used in different platforms. So you can develop for a game, for instance, there's a whole game developed in NIM, which they use this to kind of make the JavaScript side and the desktop side on the same code. And also it will add when you compare it with C or C++, it will add a lot of checks, runtime checks for buffer overflows, for stack overflows, that kind of stuff. So it will, in a sense, it will add a layer of security on top of the performance that you can get from the C or C++. So as a reverser, as you can see, it's really fun when you're trying to find your code and you have a main which calls another main, which calls another main, which then will go finally to the main. So at this point, it's really hard. Well, either you have enough patience to start to follow all the code, or you'll be losing a lot of your time just trying to find where the code actually starts. And this is just a little sample. He will show you the hard part when there's a lot more call-outs before you get to the actual user code. So this is why NIM is really powerful for the developers, but it's really a pain for the reversers. If you are more interested, you can, this book seems to be really interesting. I didn't read it, but seems to be really good according to Holger. It's really good to help you get started with NIM. Now, about the compiler flags, just for you to understand how complex this can be. So these are all the kind of compiler flags that you can have. So for instance, you can optimize for speed, or you can optimize for size. You can do a lib or a static lib. And then you can pass on all other flags so that you can strip the symbols, not strip the symbols, all the normal stuff. And you can also pass on options that will go deep into the compiler from C, not really from the NIM compiler, but the C compiler, or to the linker. So there are all these kind of options, which in the end what will generate is that just with the tests we did were just with a couple of, with speed and size, and with a couple more options on the stripping symbols or for release or not release production, and you have 60 different versions of the code being generated. So if you ever tried to make a flirt, for instance, an either flirt signature for this kind of stuff, and you have different binaries being generated by different compiler flags, it becomes really, really difficult for you to identify the actual library functions from the libraries so that you can distinguish the user code from the library code. And this is one of the things that we actually found out when we started the project was, okay, we want to be able to see what is boilerplate code from NIM and what is code from the actual developer, so that you don't lose our time looking into that kind of code. And we figure out that depending on just one little switch in the compiler, it will generate so many different things in the binary itself that it becomes really hard to actually create these kind of signatures. And then, of course, there are the calling conventions. You can pretty much use any kind of calling convention inside NIM, which makes everything, again, really more complex when you are trying to reverse it. I won't even go through all these lists to you. It's just too many options. And of course, by the time that you are finishing all of this, we can still implement all the obfuscation techniques that you might get on a C binary. Because in the end, this is C code being compiled. So if you had already figured out everything about the NIM, whoever is doing malicious code or not, they can still add other layers of obfuscation and optimization, which might be dangerous. So if you have the compiler from NIM doing all sorts of optimizations, and then you figure out, okay, now let me add more optimizations coming up from the C compiler, you might get into a point where they are de-optimizing what was already optimized, because then you have two different compilers trying to do their own optimizations, or their own checks on buffer overflows. So there is some risk here. But still, for reversers, it's a nightmare. So why did we wanted to talk about NIM? First of all, well, it's cool to reverse new languages, to understand new languages, how they work, how they are written, their syntax, or not. It depends on what you like, really. To me, it was kind of a nightmare to looking in this all new syntax, this all new metaprogramming, but yeah, it was a cool project. On the other side, there are more and more offensive tools written in NIM. Right now, there are syscalls written in NIM. There are full malware implants with C2s and with the implant for the system written in NIM. There are a lot of malware being written in NIM. So it becomes interesting for us to actually have a good way to reverse it when we come up with it. There are a lot of implants right now and obfuscators, which just wrap around other malware, which is enough for most of the EDRs not being able to pick on it. So that's that was our main motivation, was actually being able to reach that kind of code. This is just a screenshot I took from VT yesterday. So for the last, just for the last month, there were around 200 to 240 new malware samples written in NIM just for the last month, with more than 5 detections. So it's a growing, I'd say, a growing community writing stuff in NIM, and especially on the malware side, there is more and more. So let's look into the binaries. I will start with the easy stuff, which is strings. We always like strings. When we start to reverse, we like to be able to understand them. And of course, NIM being NIM, it could not just have the simple strings. So for some reason, they decided that the best way to implement a string is with a structure of 3 quad words at the beginning, one which has the size of the string, the other we didn't really were able to understand what it does, but it's there, and then the other one and then the third field is where the string actually starts. So this is basically what you can see here, and then we have our string here. And for some reason, this is no longer, so there's no, although we kind of caught it here, there is no null byte at the end of the string because they have the size. So all the strings in NIM are listed like this, as a structure of 3 fields. The reason for that, I really don't know. I would say that it may make it easier to use between Unicode strings and ASCII strings, but it's beyond what I really know why the decision was this. So what we did was that for IDA, we defined the structure, and that would allow us to actually see all the strings inside the binary. And now I will pass it on to Holger for the real complex stuff.
Okay.
There we go.
Thank you. Okay. So maybe one word to the little IDA script which I wrote to parse the NIM scripts. It is also adding the structure. So it is doing some guessing if it is a NIM string or not. So there's a chance that it might miss a few strings. So if you later on in your analyzers find a string which was not automatically found, then you can still do a right click and assign the structure to it, and it is working. And as you can see, it is also renaming the memory location. So if you're passing through the code, you have a good idea of where the string is actually used. Okay, so let's look a little bit deeper into the initialization routines NIM is using, and no worries, I'm now not digging into every initialization routine, and especially for the last rows here in the room, don't worry if you can't read these screenshots. They are mainly meant to be a reference for you when you are at home and you want to reverse a NIM binary, that you have a kind of map how you finally get to the NIM main module, which is actually the user's code, like Vitor mentioned earlier. So if I'm using the term user mode, user code, I mean the code which was written by the malware author. So pretty much all the code which does not belong to the runtime or other libraries. Okay, so our goal is to find this, and you can follow these steps depending on the different compiler flags. These are looking similar but different. And if you played a little bit with it, you're getting a feeling for how you can reach at the end the NIM main module, which is then including all the user code and a good starting point. Just one warning, as Vitor said, NIM is getting compiled from NIM into C or C++. So you're ending up with C++, which is then compiled to binary. So there's absolutely nothing which stops you to go into these initialization routines and modify them. So just in that a few jump somewhere to another routine which is doing some nasty thing. So don't be too sure that this is really the starting point of your malware. In most cases, it is probably, but if the malware author is smart, he might or she has manipulated one of the initialization routines from NIM and is executing something there. We all remember the TLS tricks people did, and I think this is quite similar for NIM. Okay, so if we are compiling the binary in debug mode with no optimization, the graph overview looks approximately like this. So it's an average function, it's not too big, and what you can see here, I have highlighted two basic blocks in yellow, and the first one points to where a string is loaded, and the second one points to where the call echo bin save function is used, which is the print function in NIM. So if you want to print out a string, you're using the echo function, which is under the hood called echo bin save. And the interesting part is in the source code, it's one line, and it's also pretty close here in the graph overview of the function from IDA. The same applies, this is a Zoom version for the for the people in the back rows. You see they are pretty close by. If we are changing the compiler flag to optimization for size, then of course the basic blocks are changing a little bit in the function, but the two functionalities, the loading of the string and the call echo bin save one, they are still pretty close together. That is changing if we are compiling it to speed optimization. First of all, you can see that NIM is adding tons of boilerplate code. It's almost 3 times the size of what we have seen before. And you can also see, let me go to the Zoom version, you can also see that the loading of the string and the actually call to echo bin save, there's a lot of boilerplate code in between. And of course, this is like spaghetti code, can be quite confusing if you're reversing that. Of course, you can also compile it in release mode, and you can use the same flags in release mode. So they are acting more or less the same. If you don't use any optimization, they are quite close. If you're using optimization by size, they are still quite close. And it is in release not as bad as it is in the debug version. They are a little bit away from each other, but not as bad as in the debug version. And while I went through the different compiler flags, you also might have recognized that these initialization routines have slightly changed. But the details of that is your homework. So when you're at home, you can have a closer look how they are changing. At the end, it's quite similar, but as I said, not the same. Okay, so welcome to the real world. Thanks to the different compiler switches and the option that you can, of course, still manipulate the C code before you are compiling it to binary. There are some NIM binaries out there which don't have a NIM main function at all, or at least IDA is not recognizing it. The way how you can still find the beginning of the user code is that you are looking for this NIM register global marker function, which is also an initialization function, which is usually used in the NIM main module function at the beginning. Just initializing some variables and so on. And if you're searching for that, and if you go to it, you can check the X references. And the function which the most X references are pointing to is usually the NIM main module function. And with this, you have a shortcut to find the user code. Even that is not always working, but at least in most cases. The good thing is that we still have enough stupid malware authors out there, so they are forgetting to strip the binary, and no matter which kind of compiler flag you're using, at least regarding the basic ones, the NIM compiler always compiles the symbols into it, so you can just read the draft infos with IDA and all the functions getting named and all the symbols getting named. So you have an easy way to just search for the NIM main module function or for other things. But again, that's just a subset of malware authors. There are still enough which are smart enough to strip the stuff, and then you're on your own. Okay, so everything we have mentioned so far was pretty straightforward and easy to develop. And at that point, I thought, oh, cool, that was everything was easy, and now let's build some flirt signatures so that we can find all the NIM library code in our binaries. And that was at the point when the nightmare started. So first of all, I assume that the majority of you probably know what flirt is, but for those who don't, flirt is the fast library identification and recognition technology which comes with IDA. It's nothing else than signature files which are describing the functions. Yeah? So this is a technology which is resolving some anonymous memory location to something like memcopy or the name of the library function. And it helps you to differentiate between interesting code you want to analyze or code which you might want to skip because it's just a library function. So this is flirt. And IDA comes with, I don't know, hundreds of flirt signatures out of the box. And for the normal stuff, that's good enough. But in some cases, you need to build your own flirt signatures. So for example, if you have a malware binary which is using a specially compiled OpenSSL version, which they statically compiled into the binary, or if they are using some SQL-Lite stuff which they have compiled directly into the binary. So there are a lot of cases where the out-of-the-box flirt signatures just not detect the library functions. And in the IDA SDK, you will find a couple of files which are helping you to create these signatures. Yeah? So you have, for example, the PCF.exe file, which can convert COF files, also, for example, object files, into so-called PET files, pattern files. And these pattern files then can be compiled, one or multiple into a signature. And the signature, finally, you are copying to your IDA Pro directory into the SIG folder, and then you can use them by file load file flirt signature inside of IDA. And then IDA is doing the magic analyzers and tells you, okay, this call to XYZ is actually a call to some certain library function. This is how it works. And the other thing, which is probably difficult to see here, at least in the back of the room, the way a flirt signature looks like is like this. It usually starts with the function bytes, the beginning of the function. If you have something which is filled dynamically at runtime in a function, then you're using a placeholder, like you can see here, the dots. Then you have the length and certain hash, which is describing the body of the function and the calls it is using, and then you use the tail of the function to finish your signature. And this is how a signature for a certain function, like echo bin save, that is our function, would look like in the signature file. Just to give you a little bit background about flirt. So, great. We did that before with OpenSSL, with other libraries which the bad guys used to build our own libraries. So I thought, hey, NIM is open source. Cool, so no problem. I'm just building a NIM library and I'm converting it to a signature. No. Because the object format which it is using is missing a couple of informations, and I discussed that with Igor from Hexrace. There's probably no way that the PCF and the PCF exe will be able to map the right patterns into the file. So I can't follow the normal default way to generate a signature. So I went back to research and thought, okay, what other options do I have? And while I was looking into the NIM source code, I saw that there's actually a NIM RTL.nim file, and like the name says, it is the runtime library, which you can build into a DLL. And most of you probably know that there is a nice plugin from Mandiant, which is called IDB2Pet, which is able to use an IDB and convert it into a PET file, into a pattern file. So the idea was to generate just a binary which I can load into IDA and then export it to a PAT file via this plugin. Unfortunately, that doesn't work because the RTL libraries or the runtime libraries, they are using certain pragmas, which leads to different code. Yeah? So if I go to the Zoom version of that, you can see that it is adding some additional code to the function. It's both the echo bin save function, but this side is coming from the NIM RTL, and this side is coming from a test source file where I'm just using the function. Unfortunately, from a binary level, they look different. You have a different stack, you have additional calls, and they are just not matching. So they are useless for any kind of signature writing. So that attempt failed too, so I had to look around for something else. And the third try, my third attempt was that I found out that I can use certain pragmas to force the function is getting written into the export section of the binary. And so the idea was to add these pragmas into all the functions inside of the standard library files and then compile it, and then I have them all in the export table. Unfortunately, again, that doesn't work. It was a pain in the neck to write a parser based on regex, which was going through, let me go one back, which was going through the original files and change these pragmas to my pragmas, because some functions don't have any kind of pragma, others have, some are distributed over multiple lines, and so on. That was already fun, to write regex regular expressions for that. But nevertheless, it didn't work like I just mentioned. So I ended up with the last solution, which has to work. So I built a really huge, or I tried to build a really huge, large source file, which includes all functions and all calls to these functions, which I can find in these standard libraries. So I wrote a parser which parsed these standard libraries. It is looking for the functions, which, by the way, can be called proc or func in NIM. And then it is extracting them. It is looking for the arguments, what type of arguments are used. It checks if it uses generics, and it is parsing the return value. Which sounds pretty cool and easy on PowerPoint. Is a pain in the ass and probably took me 1.5 weeks to build. This parser is probably the worst Python code I ever wrote. It is one of these typical POCs which grow over time, because initially I thought, okay, I just pass a certain subset of functions which are important for reversing, but then I recognized, oh, my regular expressions doesn't work. I'm not passing enough functions with that. So at a certain point, it got too complex for normal regular expressions, so I moved over to PyParsing, to the PyParsing module, which makes it a little bit easier to pass programming languages and other stuff, but it was still quite complex. And I added types and functionalities step by step, as long as I was satisfied by the amount of functions the parser was able to recognize properly and convert into something you can see here in the middle, a proper function call and a definition of the arguments with the right types. So these arguments are built, and then they are used in the function. Of course, that file doesn't do anything, and if you try to run it, it will probably crash. But we don't care about that. Yeah? We just need the generated binary code to write our signature. And hooray, after putting that into IDA, we see that these versions, the version which I automatically built from the standard libraries and the one from the test file finally are the same. Yeah? So this is now byte compliant, and now I can build the signatures out of that. But again, as I mentioned, that was really a pain to build. And just to give you a few examples of what kind of functions you are finding in these NIM standard libraries. Stuff which looks like this, with a star before the brackets, and some with a return value, some with pragmas, some with generics. Of course, all of that distributed over multiple lines in some cases. So you have so many different special characters here, for example, which are occurring. So you can imagine how painful that is to pass that to get valid type informations for your arguments. But nevertheless, at the end it worked. And I'm now parsing enough functions out of the certain libraries that I'm happy for my signatures that they are covering usually the functions which the malware authors are using. So, as you can see here, I've generated the signature file, and before I'm applying the signature, after applying the signature, and in zoom mode you can see now they are getting resolved, and you know that this is just a library call. That this is just a library call. So the next step we did was we checked that if it's also working with malware in the wild, and we picked a couple of malware from VT. By the way, I don't know if Vitor mentioned that. There's a nice trick for writing a Jara rule. If you are looking for NIM binaries, it's the fatal.nim string that is usually included, even if they have stripped the symbols. It's part of the exception handling. So it's a good way to find NIM binaries. Yeah, and at the end, same like I've shown before, the function's getting nicely resolved, and it helps us in our reversing job. In the function overview, you can also see that before applying the signatures, there's a lot of other random code. After, you can see that we have a lot of library code which we haven't had before. So it has probably resolved pretty much the most of the functions. So where are we in the moment? This is an ongoing research. So we've just reached a milestone, and we still want to develop a little bit more on it. One thing is I started to write a COF parser, which is extracting the stuff automatically and build the PAT files so that I don't need the workaround of launching IDA and leveraging the plugin and so on. But the thing which stops me in the moment is that it is extremely difficult to find the end of a function. If you have looked into symbols in a PE file, you know that it has a start of a function, but there's no information about where the end is. And that is probably one of the features the big disassemblers coming with, like IDA, for example, that they have all the logic on board, that they can recognize functions, and that they can tell where the function starts and ends. But of course, they'll need a lot of logic for that, and everyone who looked at obfuscated code knows that often enough they are wrong with their assumptions. So it's definitely not an easy task to find the end of a function. I have some ideas because I'm able to compile the stuff on my own. So one is, for example, to use the fstack protect compiler flag, or another is the function section one, which might give you an information for me where the actual function ends. I think the function section one is not really working because on Windows it behaves differently than on Linux. On Linux, it is really generating one section per function. And the initial idea of it is that the linker can just pick the functions which are really needed in the program, and it can leave out all the others. So it's the idea behind this switch is to shrink the size of the executable. But of course, if I can get an executable with every function in a different section, I know how long the function is and where it ends. Unfortunately, as I mentioned, it doesn't work on Windows, or at least I was not able to get it run on Windows. So that's probably not working. The other one is adding a stack protection function. So maybe I can use that as a kind of flag to recognize that, to figure out where the end of the function is. That might work. Other approaches is maybe the runtime record in the pdata section, but then I also have to handle the redirection, the relocations and so on. So we will see. Yeah? So there's still enough to do. And another thing which I'm working on is to create a typed library, so that we not only get the name of the functions, we can also pass the arguments, and we will see that how they are used in our disassembly. Okie dokie. And there's also a small bug in the IDC script, which I'm using to automate this workaround, but this is out of scope. Yeah, that's it. And with this, I'm giving back to Victor.
Thank you very much. Well, there's not much to say. Sorry, I just want to say something. We will release all the scripts, all the flirt signatures, everything, but they will be posted on Twitter, so if you need, just pick them up, and yeah, we'll release everything so that everyone can use it. Okay?
Yeah, maybe you want to follow us, at least temporarily, on Twitter.
Yeah, probably this week we'll release it as soon as we can. Yeah.
So that is our bold try to reach the number of our followers. No, just kidding. Okie dokie. Thanks. How are we doing regarding time? I think we're good, right? Yeah.
Hi.
Yep.
Hello. I have a couple of questions. Yeah, so first of all, are you seeing in practice in NIM binaries in the wild or ones that you've built, the functions are being inlined at all?
I didn't understand. Can you repeat that?
Are you seeing like function inlining in binaries that you've built?
You mean that they are using inlining, or?
Yeah.
Yeah, that happens from time to time.
Okay, but not heavily, right?
Sorry?
Not heavily?
It happens from time to time. I don't have any statistics how often, but I've seen it. Let's put it this way.
So on some projects that do obfuscation and that do shellcode, they are more prone to have that to use assembly inline or to use other functions inline.
Okay.
We have seen that depending on what they are aiming to do, basically.
Yeah, and my second question was, you mentioned earlier in the slides that it's possible to specify, to change the calling convention that's used between functions by using a compiler flag. Are you generating different flirt signature libraries for each variation of calling convention?
Yeah, that is actually the idea why I wrote the parser. So that you had an automatic way to generate different versions depending on different compiler flags. And the compiler flags which we have shown in the beginning, they are just a very, very small subset of the compiler flags which are actually supported. If you do a NIM full help, you will probably get, I don't know, 20 sites of compiler flags. And what we have shown are just the I would say, standard compiler flags which you can play with. But there's also a lot of other stuff which helps you to manipulate the memory allocation stuff and tons of other things. Mm. Yeah, just shout and I'll repeat.
Yeah, so it's all good now. Yeah, so with the NIM compiler, I imagine that there's some code in the compiler which does parsing, right, as a first step. Did you look into whether it's possible to leverage some of the code from the compiler itself in order to use in your own parser?
So the compiler is self-contained, so it's written also in NIM, which would kind of make it way more complex for us to actually understand all the inner of the language to make the compiler itself, rather than just go with Python in a more rough way. But at least we got it out of the way and we were able to kind of get the POC. That would be the more elegant approach, but we didn't have the time to elegancy, and we just went rough and went with the Python stuff.
Okay, that's all. Thank you.
Thanks.
Actually, just to be fair, we started with regex and then moved to Python, so that was kind of a...
Daros has a question.
Two questions. One, do you expect that the increasing popularity of Rust, since it has pretty much everything NIM does, but and a lot more concurrency and whatever, it will take some of the wind out of the NIM malware sales? Do you think that's going to have much effect?
So what I would tell you is that I don't think they compete exactly. Actually, the NIM project is actually trying to incorporate Rust as a backend. Yeah. So they don't really compete. I think
I have a question. I wonder why, because why would you bother once you go to Rust? But the other question I have for you is have you tried using the ChatGPT or something to transpile the NIM to? No?
Would be an interesting project.
Okay.
Yeah.
All right.
And then the nice thing is that in NIM you have so many points where you can interact with the code and where you can manipulate code which is compiled at the end. You have so many approaches. You could use LFM later on to do some obfuscation from the C files which were generated. You can use some C source code obfuscation in the intermediate layer. You can use obfuscation inside of the NIM binaries themselves, because as Vitor said, you can import everything to NIM, which is a C library or anything like that. Yeah, it's super flexible to build really nasty code, I would say.
Yeah, it's the good thing about NIM is flexible. The bad thing about NIM is flexible.
Yeah.
So.
Thank you for your work.
Hello. So at the start, we saw your VT retro hunt where you had 250 samples or something in the last month written in NIM. Have you done analysis into those to have some insight as to who's utilizing NIM? Is it all across the board? Are you seeing it more in crimeware, skidware, APT, that sort of thing?
No, we didn't. What we did was we went into GitHub to see what kind of projects were there. And there were a lot of projects about obfuscation, about offensive tools to inject code, to inject shell code. And there were a couple of projects also related with implants and backends, where the implant is written in NIM, but the backend is written in Python or something like that. That was what we saw mostly. But there were some attacks by APTs already using NIM, not only as an obfuscator, but also as the implant itself. So we will see how it goes, but it has all the potential to be used in a malicious way, especially due to all the obfuscation and all that kind of stuff that can be done.
Yeah, and if you're looking into the binaries you're downloading from VT, you also find a lot of experiments, I would say, yeah, which are looking typically for someone trying it. So there are some hints that the Black Hat community started to play with it. So that's another reason why we think the number of malicious NIM binaries will probably rise in the future. Especially if you think about that stuff like Go and Rust is getting more and more supported by IDA and these tools.
No more questions? 1, 2,
3.
Okay. We will be around.
Thank you.
Have a nice